Okay, we are recording. We're happy to have Nick telling us about secondary representation stability for ordered configuration spaces in the one-punctured torus. Due to the technical difficulties, like we started late, so if, probably will end late, but if you have to leave early, feel free to.
Thanks, Jeremy. Can everyone hear me?
Yep.
Great, thank you. Okay, so as Jeremy says, I'll be talking on secondary representation stability of the configuration space of the once-punctured torus. And so, how do I get this? Right, so the outline. What are we going to talk about today? Well, first, just talk about ordered configuration spaces in general and the action of symmetric groups on them. Jeremy said a lot of stuff related to this in the last couple of weeks in class, so hopefully this can go pretty quickly, especially the ordered configuration space part. I'm going to talk about some previous important results, namely results of Church, Ellenberg, and Farb, and then Jeremy and Jenny on first order stability, and then later on second order stability. These results won't be stated as formally as they will later on in the talk, but hopefully they'll allow us to get a nice little grasp of this. I'm going to talk then about the categories FI mod and FIM plus mod. These are the two categories that most people seem to do work in when they're talking about representation stability and second order representation stability. They're not so bad categories, just stuff with symmetric group actions and a little extra data. I'll state my theorem, and then I'll give a rough outline of the proof of the theorem, though glossing over quite a few details. So, what are ordered configuration spaces? So the ordered configuration space of endpoints on a topological space M, which we're going to denote F sub n of M, is just an n tuple of points in M such that no two points in this tuple are the same. And so you can cut out all these points, you cut out all the places where any 2 points are the same, and you get a resulting space. We're really only going to care about spaces where M is a manifold, specifically a two-dimensional manifold. So don't really worry about anything with the topology of M. And right, as compared to a lot of things Jeremy's been saying, the order of the points matter here. So you can't just switch the points x1 and x2 all nilly-willy. That actually does something to the space itself. And as I said, points cannot collide. Previously, right, we've been allowing collisions, and by putting some structure on these points where you can say, okay, these actually add up together. That's not the case here. The points here are just by themselves no additive structure. So, right, quick little example of a nice little ordered configuration space. Well, if you have 2 points on R2, this is going to actually be homomorphic to S1. And why is this the case? Well, so you've got 2 points in R2, and because R2 is an additive group, you can just shift one of these points to the origin, and then the other point can be any other point in R2 other than the origin. And so a loop in configuration space is just some path where you start at one place and then you return to the exact same point. So if we think about this for a bit, then a loop in F2 R2 corresponds to going around the origin, because a non-homotopically trivial loop corresponds to going around the origin, because if it doesn't go around the origin, you can just shrink it, and going around the origin more than that just gives you more loops around the origin. So this is basically the exact same thing as S1, because right, we're seeing the configuration space of 2 points on R2 is really just the once-punctured plane, which again we can just retract to being S1. A little bit more complex example, here's just a nice simple point of the configuration space on 4 points on the once-punctured torus. Just see the points, they don't collide, and this isn't really supposed to be a boundary component. It's more supposed to be going off to infinity on the right, but hopefully that's not too distracting. It doesn't really make too much of a difference here. We just don't want to ever have anything go to this looks like boundary, but rather point at infinity. So because we're dealing with ordered configuration spaces, we want to say, well, naturally there's a way of going down 1 degree and not just for getting a point. So going from a configuration space of n points to a configuration space of n minus 1 points. But when n is an open manifold or non-compact, there's a nice inclusion of an ordered configuration space on n points on M into the ordered configuration space on n plus 1 points. And to do that, you just retract near m near infinity, or the boundary if you're going to think of it as a boundary, and you add a new point in the retracted space. And this new point really you're adding is more something that looks like an R to the D dimensional space where D is the dimension of your manifold, and you're choosing some explicit point in there. Some things to note, I is not canonical. And why is this not canonical? Well, you've got a lot of choices here. If your manifold has a bunch of parts where it looks like should be boundary or going off to infinity in a bunch of different ways, well, you have a choice there which part to retract. You have a choice where to put your manifold and where to put your point in this part of the retraction, and a lot of choices. But in the end, these choices really don't make too much of a difference for us. Moreover, these inclusions induce nice maps on homology. So just fixing k for any k, we now have a nice inclusion on this homology. And basically the idea here is you choose whatever homology you're getting, and then you just add a stationary point, and that shouldn't raise the homological degree, but it increases the number of points by 1. And as I've kind of said, choice of I doesn't really matter. It does to an extent, but it's not nothing that we're ever going to actually worry about. So what does I look like in general? Well, for 4 points on the Once-Punctured Torus, we can see we just pull everything back, we pull everything away from this infinity, and then we add a new point labeled 5 somewhere in this new collar neighborhood of the infinity or the collar neighborhood of the boundary. And this gives us a nice little inclusion here. But as you can see, you don't really have any canonical choice here because, I could have chosen 5 to go anywhere in that little collar area. It would just kind of, it's a choice. But in the end, homotophically, it doesn't really make any difference. And so what can we say? So Sn, the symmetric group on n letters, is going to act on Fn by permuting the indices. So S2 acting on F2, it just changes the coordinate x1, comma x2 to x2, comma x1. And this action will nicely extend to an action on the homology groups. And this is just induced by this action by permuting indices. Moreover, this action, and this is what's important for us, is going to make these homology groups of the ordered configurations into symmetric pure modules. And that is something that is going to be exploited and talked about quite a bit. So now we're able to state a rough idea of what first order representation stability is. So this is a theory of Churchill and Burgard-Farb in the oriented case, and Miller and Wilson extended that to the unoriented case, I believe. I don't know if what else it was extended to, but so if M is a connected non-compact D manifold with D greater than 2, then in this range where K is less than n minus 1 over 2, otherwise basically saying you have at least twice as many points as the homological degree you're caring about, then this inclusion of homologies induced by the inclusion map on configuration spaces, if you permute all the indices that you get from that or use this permutation action, then you're going to get everything that you want on the inclusion. So you're saying there's really not too much added here. You just need to change some names around. This is a little bit weaker of a statement than the actual theorem because you can actually say some things in terms of SN representations. And I'll get to that later, but I want to say a little bit more about FI first. And so this will actually give us a little bit more about the structure of these homology groups as general modules. Okay, so yeah. Another inclusion. So just like we included 1 point, there's really no problem including 2 points. And so this inclusion map, as I stated on the picture here, right, is really more of an inclusion of n points on M and 2 points on R to the D, where D is the dimension of M, into the ordered configuration space of n plus 2 points on M. And right is very similar to I. All you do is pull back a little neighborhood near infinity and add 2 points. Kind of. So again, because you're making this choice on what part of infinity and how you're going to add these points, it's not a canonical choice, but still, we do get these nice maps on homology because, well, nothing really too bad happens. And so this iota prime induces a map on homology, as I stated, but note here that while we're going to increase the number of points by 2, as kind of expected because you're adding 2 points, you're also increasing the homological degree by 1. And this is because iota prime really corresponds to taking a class in homology, the kth homology group of the ordered configuration space of n points on M. And you're pairing that with 2 orbiting points, the homology group of 2 orbiting points in R to the D. So these 2 orbiting points, you could either think of as the second point orbiting the first point orbiting the second, or the 2 points kind of orbiting each other in pairs. They're all actually equivalent homotopically, so whatever floats your boat in that video. And so we have this nice map on homology here. And again, in the grand scheme of things, the choice of iota prime really doesn't matter because we're going to be doing the symmetric group action, and you can kind of wiggle things around nicely enough so nothing too bad happens. So here's a picture. If we're going to be including 2 points into the ordered configuration space on 4 points in the torus, again, we just pull back near the boundary and we add these 2 points. Yeah, and as we note here, right, it's very important that the once-punctured torus is a non-compact manifold. We can't do this without that. And right, this was something I think Zach was saying in his talk, right? It's important. It's hard to extend, and in my case, I don't know how to extend things any further. So now we can say something about second-order representation stability. And so Jeremy and Jenny proved that if M is a connected, non-compact, finite type 2 manifold, then there's some nice increasing function such that in some range, now a little bit bigger than the previous range. If you take the inclusion of the induced inclusion of n minus 1 points into n points, the order configuration space on n points, and you take the inclusion of n minus 2 points into n points, then you get all of the homology. So this just says, now instead of just going horizontally in some diagram where you're increasing number of points, you can say you've kind of got this little extra area where you can say extra information about the previous stuff. And in reality, all this is saying is when you have enough points compared to your homological degree, only really 2 things are going to be happening. Either you add another point and nothing changes, or if you looked at one smaller homology degree and added 2 points orbiting each other, these 2 cases would give you all that's possible up to relabeling of the coordinates. So we've considered all possible cases here. And this is saying this condition Rn, yeah, it's a little mysterious. And it's some function, don't really know what the function is, and that really depends on the manifold. But you can say after a while, you know you have enough points to like do everything. And based on this, right, they did a couple calculations. So this is for the calculation of R2. And so what is this theorem saying here? It's a lot of stuff going on. All that this is really saying is if you have 2n minus 2 points, and they're an element of homology on Hn1, And so really this is just saying you take your 2n minus 2 points, you pair them all off with a friend, and you make all of those friends dance around together, then dance around with each other, a nice little duet, partner duets. Then the size of this space is going to be 2n factorial over n factorial over 2 to the n. And something we can say here is, well, actually this calculation has been done out because, well, we know actually all the homology groups of the ordered configuration space of any number of points on R to the n. But nonetheless, we've got this thing that's kind of free. And this freeness is just saying you add 2 more points, the only thing they're going to be doing is really dancing around with each other. They ignore all the other points, and that's all that's really going to happen. As I said, you can say more as S2n representations, but I'm not going to say any more now. It's just, if you know anything about Young tableau, there's a nice way of drawing the Young tableau that correspond to these representations, and they have to have a very nice property, namely there's some diagonal slope -1, and if you reflect the Young tableau across that, you get the same Young tableau back over.
Maybe I'll cut in for just a second to make the comment that probably this theorem should be attributed to Fred Cohen or something, that we did not in fact do this calculation. We just related it to the secondary stability map.
Yeah, you're right. There should be a third equality or second equality or equivalence here that I'll at least state what that'll be later on in the talk. But it's what it'll in the end it'll be is something like a free FIM plus module, and that's really how secondary representation stability at least was stated in their paper. And I don't really know of a much nicer way of doing it because TCAs scare me. And right as I was saying, this module is free, and this is really free as what we're going to call an FIM plus module later on. And if we think about this together, this is probably the nicest way of doing this is, well, we've got this picture, right? So the blue corresponds to the first order representation stable range. The light green and the dark green are these FIM plus modules. We don't quite know what they are yet, but we'll do that soon. And then the dark green arrows say, okay, here's where we have second order representation stability. And this FI degree n here, really just think of that actually as the number of points in your configuration space. So okay. So now with all this in mind, I'm going to state my theorem before we get into really any details. So if T naught is going to be the once-punctured torus, then for n equals 2, the symmetric group action on these points here, just the including of 1 point, does not give you all of the nth homology of the order configuration space of 2n minus 2 points on the once-punctured torus. So what this is really saying is, well, adding 2 points is going to give you something new. That's what this first line is saying. It's 2 points orbiting each other does give you something new. Not everything just comes by putting in 1 point and letting it chill out by itself. We do actually gain some information from this second order stability map. What the second line says, so for n greater than 4, we have this equality. What this is really saying is that this is going to be generated in degree 4. So once you get past n equals 4, the only really new thing that's going to be happening are 2 points orbiting each other. You don't get any more interesting topology from the ambient once-punctured torus. Everything just comes from 2 points orbiting each other, and adding more copies of that. Moreover, this first line also says so that the secondary stability maps, right, they're non-zero. Later on, and I guess I don't state that quite here, it turns out these things are not free too. So there are going to be some relations on adding 2 points orbiting each other. Specifically, once you start adding 2 points orbiting each other and another 2 points orbiting each other, and so on and so forth, there has to be some relationships here. And I don't quite understand these relationships, but they're just nice little properties of some combinatorial analysis. Okay, so any questions about this so far? Okay. So now let's get into actually the nitty-gritty details. So what is the category Fi? So Fi, the objects are finite sets, and the morphisms are injections. And well, this is a lot of stuff, and to be honest, we don't really need all of these sets. We can just say we're only going to consider the skeleton category where the sets are the sets 1 through n, and the injections are the ones that follow from those. This is a perfectly good skeletal category. You have a nice equivalence there, and you can do everything that you can do in Fi by only considering these sets indexed by the natural numbers and 0. Moreover, if we think about it, the only injections from a set of size n to a size n are going to be also surjections as well, and so bijections in the end. And the bijections on the set 1 through n, well, that corresponds directly with a symmetric group on n elements. So we can see the symmetric groups act nicely on these finite sets and these injections. So we can think about Fi as kind of a bunch of, as these collections of endpoints and some maps, and we know that symmetric groups are going to act nicely. So in and of itself, Fi doesn't do too much. But we can consider maps from Fi to a bunch of different things. Namely, we can consider maps from functors from Fi to the space of R modules, and this will give us Fi modules. Similarly, we can consider a covariant functor from Fi to the space, the homotopy category of topological spaces, and this will give us Fi homotopy space. And notably, these are going to be the things we really care about and the things that we can do work on. And this is how we're going to be able to define first order representation stability a bit more rigorously. Okay. And so, right, because V, so some Fi module, there's going to be this nice action of the symmetric group on the set, the symmetric group on elements on the set 1 to n. There's also going to be a nice symmetric group action on V sub n. So where V sub n is the image of the set n into the category of R modules, and V is this V is the element that's sent to by where n is sent to. So any Fi module is going to be a nice sequence of symmetric group representations. Moreover, the inclusion map where we include n into m, and so m must be at least the size of n here. This inclusion map must be Sn equivariant. So we can do some permutation on n, do the inclusion, and then do the reverse permutation, and we'll get the correct thing. Nothing too wonky, nothing wonky is going to go on here, and this is nice and happy. And right, this also carries through at the level of modules. Moreover, there's a little extra structure here. When you have the action of these remaining m minus n elements on the image of some of that Sn representation into the Sm representation, this group of size m minus n, the symmetric group of size m minus n, that has to fix the image. It can't do anything else here, and that's rather important for us because it says, okay, this lives nicely and nothing crazy goes on. And so we can see, or at least I'm going to hope that this is not too bad, is if you take a homology groups, the homology groups of an Fi homotopy space, these are going to be Fi modules. And this really just corresponds to saying, oh yeah, homology is a nice functor from homotopy spaces to R modules. And so you're just combining the functor from Fi to topological spaces with a functor from topological spaces to R modules. And okay, so let's consider some Fi modules here. So perhaps the nicest and easiest to at least deal with, in my opinion, that's not just straight up trivial. We say Vn for all of the n is going to be z to the n, and we have this normal permutation representation of Sn. So right, a trivial representation and a standard representation, and the maps come from the natural inclusions. And so we can see pretty quickly, so if we include n coordinates into n plus 1 coordinates in the normal way, then if we do this a couple times, well, the symmetric group action on the remaining thing still fixes everything else. Fixes the image because, well, you're just permuting a bunch of it, like an independent vector space, and nothing bad happens. Similarly, right, it should be pretty obvious that these inclusions are Sn equivariant. Okay. Another slightly more complicated of an Fi module is you just take some sequence of Sn representations and all the maps are 0. And so if we think about this, well, if we act on Sn by Sn on Vn and include it, it's going to be 0. And similarly, if we include Vn and Vm, that's going to be 0. So Sn acting on that will be 0. So we're guaranteed the equivariance property, Sn equivariance property that we want. Similarly, we can see the action of Sm minus n. That thing is also going to be, that's also going to stabilize the image of Vn and Vm. Because, right, well, it's just 0, and you better hope this symmetric group is not going to move 0 around. Finally, and perhaps most importantly for us, if M is an open manifold, then F, the ordered configuration spaces of M, this is going to be an Fi homotopy space. And right, we need this homotopy here because, right, it's not just you making a lot of choices here, and things go wrong if you start doing these Sn actions without this homotopy. So, right, by this very last bullet point on the previous slide, this is going to be an Fi module. And these maps are going to be induced by the inclusions I talked about at the very beginning. Namely, you're just adding one more point by retracting somewhere near the open part of it, or the point of infinity, or like color neighborhood near the boundary, quote unquote, and just adding a new point there. So let me see where am I in the slides. Okay, so now we can consider the Fi homology. And right, this is not directly related to these homology groups that I talked about on the previous slide, but rather something different. So the most important Fi homology group for us is going to be the 0th Fi homology group. So the 0th Fi homology group of an Fi module V in degree M, we're going to note this H sub 0's superscript Fi of V sub n, are the Sn representations not arising from the Sn minus 1 representations. So these are going to be the new interesting things that happen in degree n that don't happen because something really similar to happen to them in degree n minus 1. In reality here, this backslash, the stuff to the right of that, I could really just replace that with the induced representation Sn from Sn minus 1 on V sub n minus 1. This is just the new stuff that's really not gotten in the previous way. So what are some nice examples of this? So yeah. what are some nice examples of this? Well, in this first case of the thing we were talking about, on the first example of an Fi module, right, where Vn is z to the n, and this is just the permutation representation of Sn, then all of these zeroth Fi homology groups for n greater than 2, they're going to be 0. And this just basically says nothing new happens under the sun. The only two representations you're going to be getting in the Vn case are going to be the induced or the trivial representation and the standard representation, because those make up the permutation representation. And the two of them are going to be there from the first stage on. If you want to get really sneaky with this and talk about Young tableau, all this is saying is all the tableau are gotten by taking one box and then just figuring out all the ways of stacking, adding n-1 new boxes such that no two boxes are in the same column. And that just gives you two different classes of representations, namely the trivial and the standard. Now, in the second example, we have kind of the exact opposite case. So if all of these maps are 0, then nothing from Vn is going to matter in Vn plus 1. So nothing in Vn minus 1 really does anything to Vn. And so these zeros Fi homology groups just spit us back our Vn. And so, right, these homology groups are a good way of thinking about what happens from our maps. Giving us nice thoughts about how this corresponds to these the symmetric group representations. And so we have our third example of Fi module, right? These homology groups of the ordered configuration spaces. And well, it's a bit harder of a question to say what are the 0th Fi homology groups. This is a bit more challenging of a question, and right, I don't really know of some way of calculating this out everywhere. But we will be able to say something nice in a few minutes once we restate what first order representation stability really is. So before I do that, I want to say a few words about symmetric group theory, representation theory. So irreducible representations of Sn correspond to decreasing partitions of n. So why is this the case? Well, irreducible representations of n correspond to the conjugacy classes of subgroups of Sn. And there's a nice correspondence between the conjugacy classes of subgroups of Sn and these partitions of n. Because any way of partitioning n, well, that just gives you the size of the cycles in the conjugacy class. And it turns out any two conjugacy classes that have different cycle lengths, they're going to be different. And if they have the same cycle lengths, they're in fact conjugate. So, right, these lambda 1 through lambda d is allowed to vary here. And some sources like to let d go off to infinity by just adding a bunch of zeros to the right. And notably here, one thing I forgot to write is that lambda 1 is going to be bigger than or equal to lambda 2 is going to be bigger than or equal to lambda 3, so on and so forth. So this is something that's decreasing. And as I said something kind of earlier, you can have this nice correspondence with Young tableau. And in a certain sense, it's easier to do the calculations that way because pictures are nice and I like doing pictures more than I like actually thinking about hard numbers. And so what do some of these representations correspond to? So if we just have n, that's the nice trivial representation. So where Sn acts trivially on this room, it's going to be dimension 1. So when you have n-1, comma 1, this is going to be the standard representation. In Young tableau, this is a box with n-1 elements on the first row and 1 element to the very left on the second row. And this is going to have dimension n. And similarly, if we have just a bunch of 1s, so n1s there, then this is going to be the alternating representation. And there's a bunch of other possibilities for everything in between, but that's a bit scary, and I don't really want to deal with that, and it doesn't quite matter for us. So we want to say there's some notion of similarity between representations of n and representations of Sn and representations of Sn plus 1. Because, right, we have these notions, right, of trivial, standard, and alternating, and a bunch of other things. Well, I never said when I was defining trivial, standard, or alternating that there was really anything weird going on there. It didn't really depend on a dimension. And so this is kind of getting at this and generalizing this a bit better. And so these representations are going to be the same or belong in some same family if we have some partition, and the only way the partition changes is by adding 1 to the first element of the partition. By adding 1, you're clearly going to, it's still going to be a partition, right? Because only the first element is getting bigger, and the first element is always the biggest. So we're happy there. And so this is some notion of equality that we're going to use here. Furthermore, what was I going to say? Furthermore, right, if we're talking about this in terms of Young tableau, this is just saying you're adding a box at the very right of the first row. Nothing new. It's nice, it's simple to see, and life is happy. And we can say, well, a sequence of symmetric group representations, so we're saying n is increasing here. This is what I mean by a sequence. So it's a sequence of representation of S1 and a representation of S2, S3, so on and so forth. This is going to stabilize if for big N, all the representations are in the same family. So namely, we're just going to choose some finite set of Young tableau. And the only thing that's going to change is as a representation of Sn to a representation of Sn plus 1. We're just going to be adding one box. We're going to be adding one number to the very first the very first element of the partition. And I guess I should say, and probably should have said this a lot earlier, right? There is a very nice way of going from symmetric group representations to these partitions. And this way is, I think, I don't know if canonical is quite the right word here, but it is well defined regardless of size n. Okay, so with this in mind, we now have a notion of stability, and we're now able to much better state what is first order representation stability. So again, this is due to Churchill and Burgett-Farb and Miller and Wilson. If M is connected, non-compact D manifold with D greater than 2, then if we have at least twice as many plus 1 points as the homology group we're considering, then if we consider these homology groups, these HK of the nth order configuration space on M with Z coefficients, right? These are going to be a bunch of Fi modules and hence a bunch of symmetric group representations. Then the sequence of symmetric group representations is going to be stabilizing, i.e. nothing new is going to be happening, and we're nice and happy. So any questions about that? Okay. So now we're going to be going on to discussing the secondary representation stability. And to do that, well, we need to change our language a little bit. And we do this by introducing the category FIM. So again, we're doing finite sets and injections. But now, on everything that's not hit by these injective maps, you have to pair all the elements off. And all of the elements have to be paired off. No one can be sitting by itself in the ballroom. Everyone gets to go dance together. So what this says is we're not going to allow maps. Skipped a little bit. We're not going to allow morphisms between sets of different parities because everyone must have a friend if they're not hit by the image of a morphism. And much like SFI, we just have a little bit extra data here. And moreover, this perfect matching is going to be numbered. So we're going to have some or rather ordered. If we say A is of size n, and then B is of size n plus 2k, then we're going to have k pairs. And we're going to order these pairs 1 through k. And this allows us to define the category FIM+. So it looks a lot like FIM, but now we say 2 morphisms are going to be the same. If the symmetric group SK, when you permute the ordering, you permute the elements of the matching, they're the same up to the sign of the permutation we're looking at. So we're just quotienting out a few of these morphisms and saying they're really the same. All that really matters is some sign convention. And what this is going to be important for us because it turns out this will allow us to deal with signs and homology groups. But nothing too crazy is going on here. We really just need to mostly worry about the fact that there's some perfect matching and everything else is there's a perfect matching away from the image of some injection. And again, just like Fi, we can define FIM plus modules, and these are going to be covariant functors from FIM plus to the category of R modules. So, right, we still have the fact that the sets 1 through the set of size n, that's still going to be an SN representation. And again, the only FIM plus morphism from the set of size n to the set of size n, well, that has to be an injection. So therefore, a surjection and a bijection. So the endomorphisms, again, have to be the same thing as the symmetric groups. So we can see any FIM plus module is going to be a symmetric group representation. And the only maps we're going to consider now, again, are from these sets of the same parity. So this map here from N to M, the only time it's going to be interesting is if the set N and the set M have the same parity. And well, what are some examples of nice FIM plus modules? Well, I don't really know of a ton, but I do know of one that's super important for us, and namely, that is the first Fi homology of these homology groups of ordered configuration spaces of open manifolds. So yeah, let's just soak this in for a second. And so what does this really say? It's saying, what are the things that are new when you have endpoints and the endpoint ordered configuration space in the n plus I homology, n plus I over 2 homology. So namely, and I probably should have drawn a picture of this, right? Things that are going to be new. So if we had 1 point, and we're considering the first homology on the ordered configuration space of 1 point on the open torus, then this is just going to actually be the meridional longitudinal loops. When we have 3 points and we're looking at the second homology, so we're going up by 2, we're increasing n by 2 and our homology group by 1. It turns out the only new thing then are going to be a meridional loop or a longitudinal loop and 2 points orbiting each other. Those are going to be the only new things. And for higher homology groups, well, you're not going to be getting anything new there. If you just increasing by 2 number of points by 2 and the homological degree by 1. So these are going to be our FIM plus modules and the FIM plus modules we care about. And this now allows us to state second order representation stability. So Jeremy and Jenny proved that if K is some field of characteristic 0, and M is some connected non-compact manifold of finite type and dimension at least 2, then the sequence of minimal generators, so this 0 with Fi homology, is going to be finitely generated as an FIM plus module. So what this is really saying is, after a certain point, anytime you increase n, really nothing new is happening other than 2 points are going to be orbiting each other. You don't get any extra homology from, say, the structure of the object or anything else like that. After a certain point, you've seen all of the homology groups that are you've seen all of the homology classes that are interesting. And the new homology classes, when you increase homological degree by 1 and the number of points by 2, really are all of the old homology classes and a pair of 2 points orbiting each other, just doing their own little thing. And then you just act by the symmetric group on them. And this will give you all the possible new homology classes. So in the end, really nothing new is happening because 2 points dancing around each other is what is the tamest thing that can happen. As I stated, Jeremy and Jenny did some calculations about various surfaces. And what they found was in the surfaces they considered, everything was either free as an FIM plus module, or after a while, these minimal generators became 0. And so nothing new was happening, or nothing at all rather was happening. And so thought what Jenny suggested, I don't know if Jeremy together suggested, somebody suggested to me, to see, is there something happening between this freeness or this eventually zeroness? And what we're going to consider then is the once-punctured torus and its ordered configuration spaces. So as I've been doing so far, we're going to use T-circ to designate the once-punctured torus. And because this is a non-compact manifold of dimension at least 2, we can apply Jenny and Jeremy's result to say, okay, it is going to be it is going to have its ordered the homology groups of its ordered configuration spaces are going to be second order representation stable. So we're good to go in considering that. But we need to now consider, are these homology, can we say anything about any explicit set of homology groups? And if we can, are they going to be non-zero eventually? Like, do they stay away from 0? Like, does stuff actually happen when you add 2 points? And moreover, are they not free? So we can ask, when we keep on adding 2 points dancing around each other, do any relations in homology pop up? We need to consider that question. And that's going to say, if there are some non-trivial relationships there's going to be some non-freeness. And this would give us a new kind of a set of secondary representation stability. And as Jenny said to me at one point, this kind of makes it slightly more interesting. I hope it does to you, because it does to me. So to do this, we first actually have to consider the homology groups of the ordered configuration space on the torus. And so it's a theorem of a guy named Roberto Bagaria that for k greater than 3, the kth Betti number of the ordered configuration space on n points, this is going to be a polynomial in the number of points n of order 2k minus 2. And moreover, this polynomial is always of order 2k minus 2. It never becomes 0. It never becomes of lower order. And if you think about the first, 0th, 1st, and 2nd Betti numbers, these are also going to be polynomials, but they're going to be polynomials of order 0, 1, and 3. So we wanted to use this to say, give some result about the once-punctured torus and its ordered configuration spaces. And because the torus can be thought of as the group R mod Z squared, there's a way of looking at the ordered configuration space of the torus and saying, well, the ordered configuration space of n points on the torus, that's really just a torus cross the ordered configuration space of n minus 1 points on the torus. And this is got by saying, okay, we have that the torus is an additive group, so let's just choose a nice point, shift our first point to there and make this our puncture. And then, we have n minus points that can do whatever we want as long as they avoid the puncture, and each other. But that's the exact same thing as saying, well, this is just the ordered configuration space of n minus 1 points on the torus. So we can use this fact, we can use Pagari's theorem to leverage another result, namely that the exact same thing is going to hold for the once-punctured torus. So again, the Betti numbers of the ordered configuration space of the once-punctured torus are going to be polynomial in the number of points of order 2k minus 2, as long as k is greater than 3. And the 0th, 1st, and 2nd Betti numbers are all going to be polynomial in n still, and they're going to be polynomial of order 0, 1, and 3. Okay. So we want to use these calculations to be able to say something more about the FIM plus module structure of these minimal generators, these new things. And note, we're not going to be able to say anything super explicit. We're not going to be able to break these down as symmetric group representations, but we are going to be able to calculate, do something about their degree and figure out how they're generated. So as a result, this is the theorem that I was able to prove, the sequence of minimal generators. So if we we add 2 points, so if we have n points and we consider the homology group of n plus 2 over 2, then the sequence of minimal generators is going to be finitely generated as an FIM plus module in degree 4. More importantly, or perhaps for interest, not more importantly, but interestingly, this is going to be non-zero in the long run, and it's not free as an FIM plus module. So we found something that is new, that isn't on one of the two extremum. So we're saying secondary representation stability is has a nice range of possibilities. It can really do almost anything it wants. So secondary representation stability is quite interesting now. We know it does a lot of stuff, and we can say, okay, well, what's going to go on? And hopefully that leads to more research. Right, so this is something new. And as I said, I don't know the FIM plus module structure here on these things. I don't know what these things look like as SN representations, though I can hedge some guesses. And so, really, what are these things? I want to do some explicit things. So when we have n equals 0 points, these are just the new homology classes on order 1 when you have 0 points. So not really anything there. But as soon as you have say n equals 2, and so note n here is going to have to be odd for our homology groups to make any sense. This is going to be the homology groups of order 2 where you have 2 elements. Similarly, for n equals 4, this is the homology groups of size 3, the third homology of 4 points on the ordered configuration space of F2. And so an element of that might look like 1 point going around 1 point going around a longitudinal circle, 1 point going around a meridional circle, and then 2 points orbiting each other and doing nice little things. So there's a bit of possibility there, but it turns out, once you have all of these, once you have the third homology group on 4 points on the torus, you've got everything. As soon as you start adding more points, the only homology groups that pop up when you increase homology by 1 are going to be the homology groups that correspond to your old stuff, plus 2 new points dancing around each other, up to relabeling everything. But all we're saying is the only thing that happens is 2 points like to dance around each other. They don't give you any nice new homology groups. So how do we go about proving this? So we first use the Betti number calculation that came from Pagari's theorem to say, okay, this is going to be non-zero. And you can later on use that exact same calculation to say this is not going to be free. And so why does non-zeroness follow? We're looking at 2 points here. So we're looking at W sub 2 of the torus on 2 points. That really corresponds to the Betti number calculation, namely this n choose 2k over 2. because the coefficient over this n choose 2k over 2 is going to be non-zero always for k big, that's telling us that we're not going to be eventually zero as modules. You can do some quick checking to show, yeah, this n choose 2k over 2 is really secretly the same thing as the n on the outside here and the 2 plus n plus 2 over 2. Those are really that's really the correspondence we're looking at there. Okay. What else? So we need to use this thing called the arc resolution spectral sequence to bound generation degree. And I'll talk about that more in a bit. And so this arc resolution spectral sequence, it turns out when you're looking at degree 6 and more, everything is pretty obvious. Everything, the only thing that really matters is the second page of this spectral sequence. All the higher pages don't give you anything good, and it turns out the map you get on the second page corresponds to this nice inclusion of just adding 2 more points orbiting each other and not interacting with the other points. To see that it's in fact generated in degree at most 4, you need to be able to see something about W1 of the Once-Punctured torus on endpoints to lower the bound. And all this is really saying is that in fact, so if you have 1 point, 1 point on the order configuration basis, 1 point on the Once-Punctured torus, then the only new thing that happens when you add 2 points from the first homology, now increasing to the second homology, is you take the path that that first point went around, and 2 points are just going to be dancing around each other. The new 2 points are just dancing around each other. They can't really interact in a third way. Kind of equivalently, this is saying that if you have 3 points on the Once-Punctured torus, and you consider like a bullseye where 1 point is fixed, the second point goes around it, and the third point goes all the way around those 2 without doing anything else with the topology of the Once-Punctured torus, then this is going to be homotopically trivial. So what is the arc resolution spectral sequence? So the arc resolution spectral sequence comes from the arc complex, and I don't quite want to get into details about that, but it's some spectral sequence that has a lot of nice properties. Namely, the E2 page, which is the page we're going to be greatly concerned with. The PQ entry here, well, it looks like some induced representation on this thing where this top homology group, this T on P plus 1, with these minimal generators on some set of points. So T is some free abelian group that has this kind of odd rank, but really T corresponds to a bunch of different things. But the way I like to think about it is T says you've got n points, or T of P says you've got something like P points, and all of these P points have to be moving around in some circles about each other. So say with 2 points, the only thing that can happen are these 2 points dancing. When you have 3 points, well, it turns out the only thing you can have is 3 points dancing around each other. But with 4 points and higher, it starts to get weird, because you can have something like 2 points dancing around each other and 2 more points dancing around each other, but those 2 then have to dance around each other. But that's not the same thing as 1 point being in the middle and the 3 other points all dancing around it. New stuff happens. But fortunately enough for us, we don't care about that new stuff. Or at least it doesn't really make a difference for us. And what's nice here is this arc complex, it turns out, is really highly connected. And as a result, the E infinity page for a lot of the range we care about is going to be 0. So to make this look a little simpler, here's a picture of the E2 page in general. It's got a lot of stuff going on here. Note there's nothing in this 0th row. And it turns out, for the most part, a lot of these elements are going to be 0. Most of this stuff is not going to matter for us. So we also need to consider the differentials because, well, the differentials are going to define a lot of this. So the D2 differential from the first column to the minus first column. So if we look at the thing, I don't know who's familiar with spectral sequences, but the D2 differential, you take something in one column, you go 2 to the left, so you go from the first column to the negative first column, and you go up one row. And this is just going to be some map, say from the point 1, 0 to the point -1, 1, or so on and so forth. All of these differentials are going to really correspond to just adding 2 more points that orbit each other nicely. And don't do anything else. Moreover, there's a nice way of including a bunch of points. And so we have this arc resolution spectral sequence. We can also consider it on just Rn, or Rd in this case, where d is the dimension of n. And there's a way of taking a product of 2 of these spectral sequences, and that'll map us. So if we take the product of Rd, the spectral sequence in Rd and Rm, we can map this into M. What this really is doing the exact same thing as we've been doing with the inclusion of points. It's just saying, well, it's not quite the exact same, but it's very similar to saying, we're just going to look at some neighborhood, we're going to retract some neighborhood of some boundary, add a copy of Rd there, and well, the weird stuff that can happen there will happen there. But it turns out this behaves really nicely with the arc complex and the arc resolution spectral sequence. Moreover, if T is this inclusion map, is this product map that I've said above, then the differentials in the spectral sequence obey a Leibniz rule. So when you take the arc differential of these things, then there's some sort of nice sort of commutation with T here. And finally, and this is something I used quite a bit, is there's some subset in those TPs, those top homology groups, called L of R, such that the image of L of R under dr, whoopsies, L of R under dr is the homology of this bullseye in these minimal generators. So what is this bullseye? Right, it's you fix one point, you have the second point orbit it, you have the third point orbit those two, the fourth point orbit those two, and so on and so forth. It kind of just looks, so if I skip down to the bottom of my thing here, this is what the bullseye looks like when you have 3 points. Okay, let's see. Going back. So right, that'll be something nice. And right, this bullseye is really going to be an element of that arc resolution spectral sequence on Rd. Nothing too crazy there. And so that's why we want to say something about that. Okay. So what do we do now? So we can use the Betti number to show that the only maps to this first thing, to the thing we care about. I guess I'm going to skip down to my, I guess, I don't have my picture here yet. Oh my, did I not include that spectrum? Oh, I did. So the only maps up to that top leftmost object that are going to be interesting when we have at least n equals 8 points are going to be this map from the first row to the negative first row. All of the maps D3. So D3s are going to go 3 rows to the left and 2 rows up. Well, that's coming from something that's going to be 0. Similarly, D4, which comes from the third row and goes to the negative first row, and then from the third column and goes to the negative first column and goes 3 rows up, that's coming from something that's going to be 0. And all of those things are going to be 0. So nothing new is going to be, nothing comes from those things. We also have the fact that this top leftmost element of the spectral sequence on the E infinity page is going to be 0. But it turns out that top leftmost element is also going to be the same thing as the top leftmost element right now in this picture on the E2 page, quotiented by the image of that E1 comma K over 2 element under D2. So, right, what this is saying is D2 from the first column to the negative first column that we see on this picture, the thing that's not 0, that's going to be surjective. So it's going to be everything. So that tells us that everything in this new homology group is going to be generated by the old homology group, where we're getting this new homology group that's 1 degree higher by adding 2 more points, and the only thing those 2 points can do is orbit each other. You might have some relations between them, but that new pair of orbiting points gives you everything you want. And so, I guess to finish up, right, same idea as before when we want to move now down to saying we can do that this is generated in degree 4 and not degree 6, because what we just did only in fact works for degree 6 and higher. Same idea as before. Now you need to worry about the fact that it's not, the green arrow here is not automatically 0, because the element it's coming from 0 isn't 0 when n is equal to 4. N is equal to 6 here. It's something non-trivial, and you need to worry that the thing that what happens to the thing that maps into that. It turns out that that's going to be surjective, so the green arrow is 0. And that's surjective because it turns out the homology group of this thing, the second homology group of 2 points, of 3 points on T3, the element that we represented by this thing, that's homologically 0. And that's good enough to tell us, in fact, the green arrow that we have here is going to be 0. And on the E3 page, it doesn't really matter. And with that together, we can say, okay, this is generated at most in degree 4. And I think that's it.